Oh, hi. Ooh, you scared me. Didn't see you there. Guess you made your way into the house, and must mean you're done learning about vector and parametric equations, and you want to learn about symmetric and scalar equations of lines, or what's next. So, yeah, let's get to it.
So our previous lesson dealt with vector and parametric equations, and as promised, we're going to start with symmetric equations this lesson. Symmetric equations work really good when you start with an example. Let's start with an example here. We'll just find the parametric equation for this line through P and Q. I'm not even going to worry about the vector equation, it's so similar. So start by finding vector PQ. And vector PQ is 12 minus 4 is 8. Negative 5 take away negative 1 is negative 4. And 1 subtract 3 is negative 2. So there's PQ. Of course, a good direction vector to use. We can use smaller direction numbers by dividing by 2 or negative 2. It doesn't matter which. Divide by 2, I get 4. Negative 2 and negative 1. So there's my direction vector. And I need to write my parametric equations. I'm going to use my P as my initial point. So I get 4 plus 4t, and y equals negative 1 minus 2t, and of course z equals 3 minus t. In my next step, what I'm going to do is I'm actually going to rearrange each of these equations, but I'm going to solve for t. Starting with x, I could say that x take away 4 is equal to 4t, or divide by 4, t equals x minus 4 divided by 4. Same thing for y. Y plus 1 equals negative 2t, or t equals y plus 1 divided by negative 2. I'm actually going to leave the negative 2 in the denominator there, and we'll talk about that in just a minute. And by now, hopefully you realize it's pretty easy to solve for t. You subtract 3 and divide by negative 1 in this case. Again, I'm going to leave that denominator as negative 1. So I've solved for t, and I've got t equaling 3 different things. Well, I can then take the right side, expressions on the right side, and I can set them all equal to each other. And that's what the symmetric equation is. Here it is right here. X minus 4 divided by 4 equals y plus 1 divided by negative 2 equals z minus 3 divided by negative 1. Now the reason I've left the denominators as negative numbers is, notice the denominator is 4, negative 2, negative 1. That is the direction vector for negative 2, negative 1. So when I leave them as negative numbers, I can see the direction vector very easily. The same way I can see the direction vector when I look at the parametric equations. Okay, 4, negative 2, negative 1. Now the one thing about symmetric equations, they do not show the initial point as easily. I mean, when I look at the parametric equations, I know that there's a point 4, negative 1, 3, my initial point, whereas here I have to realize it's the opposite. It's 4, negative 1, positive 3, the opposite signs there, and that's because of the rearranging. So there you go, there's your symmetric equation. Now in general, if you had any point or any line with an initial point, x naught, y naught, z naught, and a direction vector equaling ABC, then the symmetric equation would be x naught minus x minus x naught divided by a equals y minus y naught divided by b equals z minus z naught divided by c. Sorry about that mess there, but that's the general form of a symmetric equation. So in a way, I didn't actually need the parametric equations to come up with this. I could, if I wanted to, it just said, oh, find a direction vector, you've got a point, and find your symmetric equation a little quicker. Now in 2 dimensions, in R2, you can also have symmetric equations, but of course there'll be no z value. Find this next example, find the symmetric equation for the line with this vector equation. Well, there's my initial point and my direction vector. So I could start by saying, okay, x take away 1 divided by 1 equals, and now I got a problem here. I might go y take away 2 over 0 equals z take away 3 over negative 2. That's obviously, this middle guy is a problem here. So let's just erase that for now. And what we can actually do is take a look at the, so I mean our direction vector, when we have one of the numbers equal to 0, we got to be a little bit careful here. It is true. This is true right here. If you solve for t and x equals 1 plus t and z equals 3 minus 2t, those are the two expressions you'll get. Now, how about look at the y value? Y is equal to 2 plus 0t, or just y equals 2. We can't divide by 0, so what we actually do is we just write a comma, and we just write y equals 2. That's actually the symmetric equation in this case. X minus 1 over 1 equals z minus 3 over negative 2, comma, y equals 2. And you have to do that when you have a direction number equal to 0. And I will say this too, it's not necessary to write x minus 1 over 1. That's one case where you just might say x minus 1. In the next example, we're asked to find a vector equation given a symmetric equation. The first thing I notice is I think of that as being over 1. I can see that my direction vector will be 3, 1, negative 4. And there's an initial point of not negative 1, but positive 1, negative 5, negative 3. And so writing a vector equation, I can just say 1, negative 5, negative 3, plus t times 3, 1, negative 4. I get to make up my own parameter. I call it t, as I usually do. Here's a bit of an interesting question. What angle would this line, in this example, make with this other line right here? So two lines, assuming they intersect, we would say that their angle of intersection, call that theta. Okay, now I didn't actually check when I made these examples up to make sure these lines actually intersect, but let's not worry about that. We'll pretend that they do. If we want to find the angle of intersection between each two lines, that's actually a really, like if you just were to be doing old-fashioned, lines on a plane and y equals mx plus b form, finding the angle two lines make when they intersect that's a little bit of work actually. But using vectors, it's quite simple. Our first line has a direction vector equal to 3, 1, negative 4. And our second line has a direction vector equal to 4, negative 2, 0. So the angle that two lines intersect at is the same as the angle between their two direction vectors, if you just imagine d1 being here and d2 being here. Now vectors themselves don't have positions. We can think about a vector being wherever we want. In this case, we'll imagine they're right there at the point of intersection. And we need to find the angle these two vectors make with each other. Well, then we're back into the dot product. d1 dotted with d2 is the magnitude of d1 times the magnitude of d2 times the cosine of the angle between them. If we rearrange that for the cosine of the, so rearranging that for the angle, and then finding the dot product. So dotting the two vectors together, 3, 1, negative 4. We haven't seen the dot product in a while. Dotted with 4, negative 2, 0. Divided by their magnitudes. Okay, so the magnitude of d1, 3 squared plus 1 squared plus negative 4 squared. And d2, 4 squared plus negative 2 squared. So that's how we do magnitude again, using Pythagorean theorem. We came up with that formula a while ago. And of course, to do the dot product, remember you multiply numbers together and add. So 3 times 4 is 12, plus 1 times negative 2, plus negative 4 times 0. Okay, adding those together. Okay, continuing on. You're going to get G12, 10. And if you take that, plug it into your calculator, do the inverse cosine, you'll get the angle of intersection. I'm getting an angle very, very close to 64 degrees. So there you go. Now, like I said, don't worry too much about this, but I assumed that those lines actually did intersect. It's possible in 3-space that two lines can miss each other, and we're going to talk about that later on. So for now, kind of a flawed example, we'll assume that they did actually cross each other, and if they did, that is their angle of intersection. Let's talk about the scalar equation of a line right now. Now, in order to talk about the scalar equation of a line, we must first define what's called a normal to a line. So any vector perpendicular to a line is called a normal vector, or just a normal to the line. So consider this line right here. It has a direction vector of 3, 5. So what's a vector that's perpendicular to 3, 5? We'll call that a normal. Well, we know that this has to be true. In order for a vector, a normal, to be perpendicular to this line, it's got to be perpendicular to the direction vector. And we know that the dot product has to be 0, because that's how we determine whether or not vectors are perpendicular, using their dot product. So what do I dot with 3, 5 to get 0? Well, one possibility is negative 5, 3. You would get negative 15 plus 15, which is equal to 0. Another possibility might be 5, negative 3. That also works. When you dot that with D, you'll get 15 minus 15, which is equal to 0. Now, if that's our normal, technically there's a whole bunch of other normals as well that are just multiples of n1 or n2, either shorter than them or longer than them. It doesn't matter. But why would we? I mean, we could use negative 10, 6, or negative 50, 30, or negative 500, 300. But why would we use normals so large if we don't need to? We tend to choose normals that have integer components that are as small as possible. Okay, why are we going to talk about normals? Well, let's take a look at this little, just bear with me and see where this is going. Consider a line with a direction vector of negative 2, 5 and a 0.13. So we might actually imagine a drawing of that line. That line has a 0.13, it has a normal, it has a direction vector as well. Now, I can tell what the normal is. One possibility for the normal is 5, 2. Because when I dot that with the direction vector, excuse me, I will get 0. 10, negative 10 plus 10, which is 0. I could also use negative 5, negative 2, but that seems kind of strange. So that would be the normal that goes in the other direction. Okay, I'm going to create another vector that's also on my line or parallel to my line. If I have any point xy, then a point-to-point vector would be x minus 1, comma y minus 3. That is this vector that goes from, technically from here to here. It is also perpendicular to the normal, meaning if I dot it with 5, 2, I will also get 0, just like when I dotted D with n, I got 0. But now I have variables here where x and y are any point on the line. We'll expand this using the dot product. You get 5x minus 5. 5x minus 5. Oops, just give me a second here. Sorry. So when I do that, it's right. I get 5x minus 5. Okay, plus 2y minus 6 equals 0, which would rearrange to 5x plus 2y, take away 11 equals 0. Now that last line right there that I squeezed in, that is the scalar equation, or sometimes called a Cartesian equation. I believe the textbook I've given for you to work with online calls it a Cartesian equation. 5x plus 2y minus 11 equals 0. Now notice that if I were to, notice that my normal 5, 2 appeared in the equation like that. So in general, if I change the line so that I had a different normal, I would always find I get a Cartesian or a scalar equation that looks something like this. ax plus by plus some value of c equals 0. The 11 is kind of random, but the 5 and the 2 come from the normals. So if I want a scalar equation to a line, and I have a normal, it's actually really easy. I know that this, in this example, my normal is negative 3, 2, which means a is negative 3 and b is 2, meaning the equation technically is going to look like negative 3x plus 2y plus c equals 0. Now I could find c by doing what I did up here, or I could just sub the point in and say that, well, the c value's got to be whatever balances the equation, so just sub in the point negative 3, 7. And I get negative 3 times negative 3 plus 2 times negative 7 plus c equals 0. Or 9 minus 14 plus c equals 0 gives you c equals 5. And our scalar or Cartesian equation is, we might start by writing negative 3x plus 2y plus 5 equals 0. But do you remember how we're dealing with, in calculus, dealing with standard form, we always like to make the first one positive. So another scalar equation that we generally write is just this one right here. This one implies your normal is negative 3, 2, where this one says your normal is 3. Of course, those are, one normal is just the opposite direction of the other normal. They still are both normals to the line. Now, there's a few things I'd like you to think about here. First of all, you might be saying, this isn't new. Like, we've already seen equations of lines that look like this. Just like y equals mx plus b form, you know, you end a calculus question often by finding the equation of a line, and there it is. This isn't new. And I definitely agree, it is not new. It's this idea, though, that a line's direction can be described by a normal to it. That's the important part. And this other idea as well, which is, how about the scalar equation of a line in 3 space? Well, you can't do it. There's 2 reasons there's no scalar equation of a line in 3 space. Can you think about one reason? Well, imagine finding the normal of a line in 3 space. There's an infinite number of normals. I'm going to try my best to describe this, but if this picture here is now in 3 space, all of a sudden the normal could go here, it could go down, it could also come straight out of the page. If I try to draw that, you might draw it like that. It could also go straight into the page. In fact, it could go all the way around. Imagine doing like a circle here of all, there are an infinite number of normals, none of which are collinear. So there's no unique normal whatsoever in 3 space. So that's one reason there's no scalar equation in 3 space. The other reason is quite simple. If there was a scalar equation in 3 space, you would probably assume it looked something like this with x, y, and z. Well, if you were to find all of the x, y, and z values that satisfied this equation, you would find, I mean, one of them, for example, is 0, 0, 5. If you were to find all those values and plot them, you would not get a line. You would actually get a plane, a flat surface extending in all directions. And in fact, the reason we're talking about scalar equations of lines is because we're getting ready to talk about planes. And the concepts in this lesson will help you when we go to study planes. Okay, that's it for now. I'll see you next time.